This video is about addition of apparent powers. For instance, if we have a number of induction motors, so how do we calculate the total apparent power? So there are two cases. The first situation or the first circumstance is when the induction motors have different power factors and hence different phase angles. And the second case or the second situation is where the induction motors have the same phase angle or the same power factor. So how do we calculate the total apparent power in the two cases or the two situations? Please do follow me in this video, and please do subscribe to my channel. Now the examples. In the first category, we have apparent powers S1 and S2 with different power factors and different phase angles θ1 and θ2. How do we add up the two apparent powers? So we have this example for the first situation. A 230 volts 50 Hz 4 kilowatt 0.8 power factor lagging induction motor and another induction motor with 3 kilowatt 0.9 power factor lagging at 50 Hz and 230 volts are connected in parallel to a 230 volt 50 Hz MCCB panel. Calculate the total apparent power for the two induction motors. Neglect possible losses. So that is that. Then the second question is about a situation where the phase angle is the same for all the induction motors. There could be two, there could be more. So a 230 volt 50 Hz 4 kilowatt 0.85 lagging power factor and another induction motor 230 volts 50 Hz 3 kilowatt 0.85 lagging power factor are connected in parallel to a 230 volt 50 Hz MCCB. So calculate the total apparent power for the two induction motors. Neglect possible losses. The only difference between the two is that we have different power factor. Here we have different power factors. 0.8 for the first motor and 0.9 for the second motor. So whereas here in the second category or the second circumstance, we have the same 0.85 power factor, 0.85 for the first motor, 0.85 power factor for the second motor as well. Now, solution to the first part. For the 4 kilowatt 0.8 power factor induction motor, active power P1 is equal to 4 kilowatt, which is 4,000 watts. Reactive power is equal to P1. This for the 4 kilowatt motor. Alright. Apparent power S1 is equal to the active power divided by the power factor, which is 5 kilowatts or 5,000 VA. So Q1 is now equal to 3 kVAR, which is equal to 3,000 VAR or VAR. For the 3 kilowatts motor at 0.9 power factor lagging, P2, which is the active power, is 3 kilowatts. From there we can calculate S2, which is the apparent power for the 3 kilowatt motor, to be equal to 3.333 kVA, which is 3,333 VA. Now from there, Q2 is this, which is 1.45 kVAR or 1452 VAR. Now total apparent power ST for the two induction motor is vector st, which is equal to p1 plus p2 plus j q1 plus q2. That is in complex form. And from that, we can calculate the magnitude as 8.3 kVA, which is equal to 8,300 VA. And from that, we can calculate the phase angle to be tan inverse of the particle component, which is the reactive component, divided by the active component, and the phase angle is 32 degrees. Solution to the second part, where the power factor is the same for the two motors, 0.85. Alright, for kilowatts, for 4 kilowatts, 0.85 power factor induction motor, PA is equal to 4 kilowatts. Apparent power SA is equal to 4700 or 4.7 kVA. For 3 kilowatt motor at the same power factor, PB, active power, PB is 3 kilowatt. Apparent power SB for it is 3.53 kVA. So since power factors are same, being equal to 0.85, total apparent power S for the two induction motors is equal to SA plus SB algebraically. So, and that is equal to 4.7 plus 3.5 is equal to 8.23 kVA or 8,230 VA. Since I said that this is the category 2, if the power factor is the same for all the induction motors or the inductive loads, the apparent powers could be added up algebraically. So, and this is what is here. Now, it can be added up algebraically, or it can also be added up vectorially, unlike in this situation 1, where the power factors are different and the phase angles are different. So the addition can only be done vectorially. So algebraic sum will not hold for that one. But in this case, both vector addition and algebraic addition hold. So now we go to vectorial addition now. Vectorially, QA, that is reactive power QA, is equal to this, which is 2.468 kVA or kVAR. So Q2 is this one. Total apparent power for the two induction motors is in vector form, is equal to PA plus PB plus J into QA plus QB. So this is the imaginary component, and this is the real component. Alright, and then the magnitude is 8.23 kVA or 8,230 VA, which is in agreement with this. Which is in agreement with the answer in 2.1. That is what is obtained here. Alright, and the phase angle is 32 degrees. So if it is calculated using 0.85 as power factor, the phase angle is also 32 degrees. For the second category, here, where the power factor is the same for the two motors, or the phase angle is the same for the two motors, the phase angle is really phi. So what I really meant in my explanation previously is phi, not necessarily theta. Theta is for this one according to this diagram. So the phase angle phi is 32 degrees. Now from 1 and 2, from questions 1 and 2, the conclusion is that when two electrical loads have different power factors, the total apparent power can only be calculated vectorially, which is this one. Different power factors and different phase angles. You can only calculate the total apparent power vectorially. And when the loads have the same power factor, the total apparent power can be calculated algebraically or vectorially. Now finally, please do subscribe to my JK Multimedia Solutions channel. Thanks for watching.